Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about central limit theorem. Central limit theorem states that the probability density function of a sum of capital N independent random variables approaches the Gaussian density function as capital N tends to infinity. Although the theorem can be applied, although the theorem can apply to some statistically independent random variables in most applications, we use it only for statistically independent random variable. So this central limit theorem can be explained unequal distribution case and equal distribution cases. So this central limit theorem can be explained into two cases, that are unequal distribution and equal distribution. First we are going to discuss about unequal distribution. So the concept of unequal distribution, let capital N random variables xn, where small n is equal to 1, 2, 3 and so on. So there are x1, x2, x3 and so on, xn are the capital N random variables. Have probability density functions with mean xn bar and the variance sigma xn square. The central limit theorem states that the sum of the random variables yn is equal x1 plus x2 plus x3 and so on xn with mean values yn bar is equal x1 bar plus x2 bar plus x3 bar plus and so on xn bar, and the variance is sigma y square is equal sigma x1 square plus sigma x2 square plus and so on sigma xn square, have a probability distribution function asymptotically approaching a Gaussian distribution as capital N tends to infinity. So therefore, the sufficient conditions are sigma xn square is greater than b1 is greater than 0, n is equal to 1, 2, 3 and so on capital N, and expectation of magnitude of xn minus xn bar whole cube is less than b2, n is equal 1 to capital N, where b1 and b2 are positive numbers. So this is the concept of unequal distribution. Next, coming to equal distribution, let capital X1, X2, X3 and so on xn be the n number of independent n number of independent identically distributed random variables. Let capital X be a random variable and its random variable is defined as S is equal to sum of the n random variables, that is capital S is equal to x1 plus x2 plus x3 plus and so on xn. So taking the expectation on both sides into this equation, we get expectation of LHS term is equal to expectation of RHS term. On RHS side, applying the expectation into each term, expectation of sum of random variables is equal to sum of their individual expectation. So therefore, expectation of S is equal to expectation of x1 plus expectation of x2 plus expectation of x3 plus and so on expectation of xn. Since all xi's are identically distributed random variables, all are of same mean value and variance. So expectation of x1 is okay. Expectation of x is also denoted as m. So now here x suffix I are identically distributed random variable. So that are of same mean value. Same mean value mean expectation of x1 is equal to expectation of x2 is equal to and so on expectation of xn. So expectation of x is also denoted as m. So therefore, from this equation, expectation of S is equal to m plus and so on plus m is equal. So these m's are repeated n times, therefore which is equal to n into m. Okay, this is the random variable s defined. So in this equation, take the variance on both sides. Variance of LHS term is equal to variance of RHS term. So using property of variance, variance of sum of random variable is equal to sum of their individual variance. That is variance of x1 plus variance of x2 plus and so on variance of xn. So all the variants are same. So variance of the random variable is also denoted as sigma square. So variance of x1 is sigma square, variance of x2 is sigma square, and so on variance of xn is sigma square. So now here these variants are repeated n times. So variance of s is equal to n into sigma square. So sigma square is that sigma square is also denoted as variance of x, n into variance of x. The standardized random variable s dash associated with s is defined as, so the standardized random variable is defined as s dash is equal s minus e of s divided by square root of variance of s, so which is equal to s minus, so expectation of s is nm and variance of s is n into sigma square, already explained, and substitute e of s and variance of s into here, we get s minus nm divided by sigma into square root of n. So the central limit theorem states that s dash is Gaussian. To verify the above theorem, a property of moment generating function of a random variable is used. So that property of the moment generating function of the random variable property is, if two random variables are having the same moment generating function, then they are said to be identically distributed. So that is, they are of same density. Let capital X be a Gaussian random variable. Now find the moment generating function of a standardized Gaussian random variable x dash and the moment generating function of s dash defined above. If both moment generating functions are same, it can be concluded that x dash and s dash are identically distributed. That is, they are of same density using the property of moment generating function. Since x dash is Gaussian, s dash also will be of same density, that is, s dash is also Gaussian. This verifies the central limit theorem. So we know that the moment generating function of a Gaussian random variable x with a mean m and variance sigma square is given by mx of t is equal e power mt plus sigma square t square by 2. M is the mean value of the random variable, sigma square is the variance of the random variable, mx of t is the moment generating function of the random variable. Since a standardized random variable x, that is x dash, is of zero mean and unity variance, its moment generating function is. So zero mean m is equal to 0 and variance sigma square is equal to 1. And substitute m is equal to 0, sigma square is equal to 1 into this expression. The standardized random variable of the moment generating function is mx dash of t is equal e power t square by 2 from this expression. To verify central limit theorem, we have proved that moment generating function of s dash, that is ms dash of t, is also equal to e power t square by 2. Consider ms dash of t using the definition of moment generating function. Ms dash of t is equal expectation of e power t s dash. So but s dash is equal to s minus m by sigma root n, and substitute s dash value into here. We have expectation of e power t into s minus n by sigma root n. But x is equal to, but the random variable s is equal to sum of random variables, that is s is equal to x1 plus x2 plus x3 and so on plus xn, and n into m is the m plus and so on m divided by sigma root n. So the RHS term is simplified as, is arranged as expectation of e power t into x1 minus m by sigma root n into e power t into x2 minus m by sigma root n into and so on e power t into xn minus m by sigma root n. Since xi's are identically distributed, so this e power x into this within the bracket term is written as expectation of within the bracket term is written as e power t into x1 minus m by sigma root n whole to the power of n. So therefore ms dash of t is equal expectation of e power t into x1 minus m by sigma root n whole to the power of n. So this within the bracket term is written as this one. That is considered as equation 1. So we know that the expansion of the e power x is 1 plus x square by 2 factorial plus x cube by 3 factorial plus and so on. Okay. Expectation of e power t x1 minus m by sigma root n. So using this expansion, e power t into x1 minus m by sigma root n is written as 1 plus t into x1 minus by sigma root n plus t into x1 minus sigma root n whole square by 2 factorial plus and so on. So this within the bracket term is arranged as 1 plus t into x1 minus m by sigma root n. So t square by 2 factorial sigma square n into x1 minus m whole square plus and so on. Applying the expectation into each term, we get using the property of expectation. Expectation of sum of random variable is equal to sum of their individual expectation. Applying expectation into each term of this equation, we get expectation of e power t into x1 minus m by sigma root n is equal 1 plus t by sigma root n into expectation of x1 minus m plus t square by 2 factorial sigma square n into expectation of x1 minus m whole square plus and so on. So we have expectation of x1 minus m. So using the property of expectation, expectation of x1 minus m is expectation of x1 minus expectation of m. Since m is the constant, expectation of m is m. So expectation of x1 is also denoted as m. M minus m is equal to 0. So expectation of x1 minus m is 0. And expectation of x1 minus m whole square is the variance of the random variable. So therefore, applying these concentrations into above expression, we get expectation of e power t x minus m by sigma root n is equal 1 plus and expectation of x1 minus m is 0. Second term is 0 plus t square by 2 factorial sigma square n into third term is variance with sigma square plus and so on. So now here second term numerator and denominator sigma square is the cancel. The remaining RHS term is 1 plus t square by 2 factorial 1 plus t square by 2 factorial n plus and so on. So from equation 1, what is equation 1? This is equation 1. ms dash of t is equal to, then now here expectation of e power t x1 minus m by sigma root n is calculated. So from that equation 1, ms dash of t is equal 1 plus t square by 2 factorial n whole to the power of n. So taking limit n tends to infinity on both sides, limit n tends to infinity ms dash of t is equal limit n tends to infinity RHS term. So the right hand side of the above expansion is e power t square by 2, that is moment generating function of s dash is also e power t square by 2, and thus s dash is also Gaussian. So this verifies central limit theorem. This verification can be done by taking characteristic function of x dash and s dash also. So this central limit theorem is applicable whether the random variable x dash are Gaussian or non-Gaussian. This is the concept of central limit theorem.